The reaction of hydrochloric acid and sodium hydroxide is an acid-base reaction. A color-changing indicator allows us to see that a reaction occurs.
Acid and base reactions give a lot of energy to a lot of different chemical processes, as we'll see as we go forward in this class. All acid and base reactions at their core, they end up making water, and they end up making what's called a salt. And a salt is basically the other leftover of acid and base reactions. So for this one, it's sodium and chloride coming together to make sodium chloride. That's the same as table salt. But a salt doesn't have to be table salt. For example, if you had potassium hydroxide and hydrobromic acid, you would end up with KBr, potassium bromide. That would be another kind of salt. So a salt is the product of an acid-base reaction. But the important part for us is that actually just making water is the driving force. That's why this reaction happens. Now in that little video, it shows the solution turning purple, and you can make that happen. If you add a compound called phenolphthalein, it'll turn your solution kind of a pink color once the acid and base react. However, most of the time, acid and base reactions colorless. All right, so you don't see anything, you don't see solids form, you can't tell if water has formed. Sometimes you can feel heat though. These reactions give off a lot of energy when they happen, so sometimes they'll feel kind of warm. But just kind of FYI, it may look like nothing happened, but maybe something did happen. The net ionic reaction, when you have an acid and a base comes together, is almost always hydroxide plus H plus making water. So making water is important. A lot of energy is created. This net ionic equation applies to all reactions of strong acids and strong bases. We'll talk about those in just a second. Sometimes acid-base reactions are called neutralizations. When the acid and base amounts are equal, you will create water and a salt. If it's sodium hydroxide and hydrochloric acid, the salt is sodium chloride. So in theory, you could have a strong acid and a strong base react, and you could drink the resulting water because it would be like salt water. But nobody's going to try that on my watch. I don't trust anything that's been measured that much, and your life is more important to me than some silly chemistry demo. But in theory, if you do the neutralization reaction right, you should be able to drink the result, but don't try it.
Hydrochloric acid is a strong acid. The compound hydrogen chloride ionizes completely, so many ions are free in the solution.
Acids are really important to chemists. Acids always have a hydrogen listed first, and there's a lot of energy involved when you use an acid. Now, acids and bases react to make water. Anytime you can make water, you've got a lot of strong energy given off. Hydrochloric acid is a strong acid, and when you put it in water, it really doesn't stay as HCl at all. It breaks up 100% to H plus and Cl minus. So hydronium is H3O plus technically. And that's officially, in the chemistry world, what acids create. But a lot of times hydronium is just listed as H+. Now here's a list that I really want you to tune into. There are 5 strong acids, and these are really important for stuff we're going to talk about. Hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, HNO3 is nitric acid, HClO4 is perchloric acid, and knowing those 5 strong acids is going to have lots and lots of uses. All of those acids break up 100% to an H plus ion and some kind of counter ion. So chloride if it's HCl, bromide if it's HBr, stuff like that. Make sure you make a note of that.
Hydrofluoric acid is a weak acid because it only partially ionizes. At any one moment, most of the HF molecules have not split into their ions.
So there are 5 strong acids, which we talked about on the last page, but there are thousands upon thousands of weak acids, and weak acids just don't break up to the same extent that the strong acids do. So in the video right there, it showed hydrofluoric acid, HF, and maybe one of every 1,000, every 10,000, every 100,000, who knows, molecules do break up into H+, and in this case, F-, but most of them stay the same. So you don't have the the power of in a weak acid that you do of a strong acid. You don't have as much H plus to deliver. Most acids are this way, and there's some examples of other weak acids, but again, there's thousands of them. Acetic acid is the active ingredient in vinegar, so it's pretty common. Carbonic acid is something that actually makes drinking water a little bit acidic. It's totally normal, don't worry. Phosphoric acid, etc., etc. Most of the foods we eat and most of the things we drink are actually weak acids. So again, if you know those 5 strong acids, you can just assume that all other acids are going to be weak. Most of the acids will have an H listed first, but you can see there that acetic acid is the one notable exception where the H is listed last. It has to do with the formula, which you can see in the upper right-hand corner. That CH3COOH part, it's only the last H which is acidic. If you take the H plus off, you have the acetate ion, which is one of the polyatomic ions. So that's why I guess they list it that way. I don't know. As a science teacher, I would so prefer it was listed H, CH3CO2, but, nobody listens to me, alas.
NaOH, sodium hydroxide, is a strong base because it dissociates completely. In aqueous solution, it breaks into sodium cations and hydroxide anions.
Acids are strong. Bases are strong as well, but for different reasons. So what is a base? A base is a metal hydroxide. You have to have a metal, and it's next to the polyatomic ion hydroxide, which is OH minus. So just like with acids, there are strong bases and weak bases. There are 3 strong bases you really, 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 really need to know / memorize. Sodium hydroxide, potassium hydroxide, lithium hydroxide. Those dissociate 100% into the metal ion and hydroxide. So NaOH goes to just Na plus and OH minus. Same thing for lithium and potassium hydroxide. They will break up into K plus and OH minus, for example. Very, very powerful. Lots and lots of energy. And you want to be careful with these. They are just as strong and deadly, if you will, as the strong acids are.
On the left is H2O, water. On the right is NH3, ammonia. The dots and lines represent electrons. Ammonia acts as a base in water. It removes a hydrogen ion from water to create hydroxide and ammonium ions. In solutions, only a few hydroxide ions are created at any one time, so ammonia is a weak base.
Just like we saw with acids, there are strong acids that dissociate 100% to H plus and the counterion, while weak acids, maybe 1 in 10,000 break up. Well, there's also strong bases like we saw and weak bases, and all of these things create hydroxide through one version or another, but the weak bases just don't give as much. So while the strong bases, you can see the hydroxides right in there, a lot of times the weak bases don't have hydroxide listed. So the great example is ammonia, NH3, which is a real common weak base. Now, NH3 does not have any hydroxide, but what happens is ammonia reacts with water, like the video in the upper right-hand corner says. It makes ammonium, which is NH4 plus, and ammonium is different than ammonia, FYI. But anyway, ammonium and hydroxide. So that's where the hydroxide comes from, and that's why it's a base. So those examples right there are all bases. Most of the negative polyatomic ions are bases: carbonate, phosphate, sulfate, those kind of things. Hydrazine is another type of base. So notice that it's basically either a nitrogen-containing compound or a negative polyatomic ion. But here's the punchline. If you know that you have a base and it's not one of the 3 strong bases, you can assume it's weak. There are thousands upon thousands of weak bases, but only a couple of strong bases. So that's what's important. And again, strong bases give 100% hydroxide. All of these weak bases would not give the same thing. A lot of our household cleaners are weak bases. So if you've cleaned your house before, you're probably using a weak base. This is a list showing the some strong acids and the strong bases, or at least a lot of them. You can see the strong acids in the upper left-hand corner and the strong bases in the upper right-hand corner. Now again, there's just thousands upon thousands of both weak acids and weak bases. And again, most of the time, if you hear about an acid, you can assume it's weak. And if you hear about a base, you can assume it's weak unless you know it's one of the strong ones. I might once in a while share a different strong acid or strong base, but I would tell you, if it was, okay? And again, most of these are weak, so you don't see the same. But again, things like aspirin and vinegars, acetic acid, stuff like that. There's a lot of acids around us and a lot of bases, so these are important for us in life as well as in chemistry. Here's a question you might see. It says, which of the compounds below is not an acid in water aqueous solution? Okay, well, anything that has an H listed first is going to be an acid. So you can see that B, which is phosphoric acid, D, hydrochloric acid, and E, which is hypoiodous acid, a more rare acid, but they all have H listed first. Those are going to be acids. So it's going to come down to A or C. A is the most common weak acid. It's acetic acid. The hydrogen's listed at the end. I don't know why, but that's just the way it is. You kind of got to know that. So acetic acid is an acid. And C is probably the most common weak base, which is ammonia. So ammonia is a weak base. It has hydrogen, but it's not an acid. It's going to be a base. When it reacts with water, it makes the ammonium cation and hydroxide. That's where the base part comes in.